Today, our invited speaker is Professor Gianfranco Bertone, the spokesperson of the Grappa Center of Excellence in Gravitation and Astroparticle Physics of the University of Amsterdam. And he is also Associate Professor in the University of Amsterdam. He is a recognized expert on dark matter, and he has published many scientific articles on this topic, as well as a popular science book. And today, he will tell us about the current status of the searches for dark matter. So please, Gianfranco.
Thanks a lot. Thanks for the invitation. It's a great pleasure to be here. It's very good to see so many familiar faces in the audience. So you've had already in this series of colloquia, you've heard already about dark matter. And I will try to provide some complementary information with what has been already said in previous colloquia. So in particular, I will try to provide, say things that do not overlap too much with what Andreas Zucker said back in January. And so, for instance, I will not discuss axion dark matter because I know that you've had a colloquium by Frank Wilczek about that. The quest for dark matter is a very, very broad field that spans cosmology, astrophysics, particle physics, physics beyond the Standard Model, and so on. So I try to put together some material that hopefully is specifically interesting for you, for this particular audience. And the way I'm supposed to arrange this, organize the material in this presentation is by starting with a discussion about dark matter in astrophysics and cosmology. Then I will discuss dark matter candidates with our possible solutions for the dark matter problem. And then I'll focus, since Marcel Voss, who contacted me, unfortunately is not here, asked me specifically to talk about WIMPs. I will concentrate specifically on weakly interacting massive particles as candidates for dark matter. So let me start with the first part, and I would like to start with a specific point, which I think is very important to keep in mind, and is not sufficiently emphasized, in my opinion, in conferences about dark matter in cosmology and particle physics. And the specific point I want to make is that we often present the evidence for dark matter by describing what is the universe made of. And we say, the universe is made of 72% dark energy, 23% dark matter, and 5% atoms. And we always stress, atoms is, all the baryonic matter we're familiar with, and also the non-baryonic matter we're familiar with, includes neutrinos. Everything we know about the Standard Model is in that 5%. And then we said the rest is the dark universe. However, I think this is it is quite misleading to say to present things in this way, because it seems to give this distribution of dark energy, dark matter, and baryons sort of a fundamental status, something a fundamental truth about the composition of the universe. However, as probably many of you already know, this composition has changed in the history of the universe. So it is true today that dark energy, for instance, contributes 72% of the matter and energy budget of the universe. But if you look back in the history of the universe, and in particular if you're interested not in the dynamics of the universe today, but if you're interested in questions like how structures formed in the universe, how a galaxy like a Rome, like the galaxy we live in, has formed, then that's completely irrelevant. The fact that dark energy is dominated the dynamics of the universe, and the universe is accelerating today, is irrelevant for understanding how a galaxy like Rome formed at very early times in the history of the universe. And in particular, if you look at the distribution of dark matter, dark energy, and normal matter, back when structures started to form, so essentially at decoupling, right after matter radiation equality, the distribution of matter and energy in the universe was completely different. And that's perfectly understood in the context of standard cosmology. But I don't think this point is stressed enough. If you look back at decoupling, then you have still radiation, so relativistic particles, photons and neutrinos, which are still around because they haven't been redshifted away, essentially. And then you have matter in the form of atoms, and so baryonic matter and dark matter, that is really responsible for the growth of structures in the early universe. Okay, so what we may approximately constant throughout the history of the universe. So if you want something fundamental to keep in mind, if you think about how the history and the dynamics of the universe, is the ratio between the amount of dark matter in the universe and the amount of baryons. So how much dark matter we have and how much normal ordinary matter we have in the universe. And this has remained more or less constant throughout the history of the universe. And this is either kind of perfectly true or very close to be true. We can constrain this the possible variations and departures from this constant ratio between dark matter and visible matter. So I will not review the evidence that we have for dark matter today, because it would take me too long, and I think there are more interesting recent developments that are worth discussing with you today. But let me just say that we have evidence for this additional component of matter, essentially on all astrophysical scales. Starting from the scales of galaxies, rotation scales of galaxies, actually even locally, and I will say a few words about the local dynamics of stars in the solar neighborhood, all the way to stars, rotation scales of stars and gas in galaxies, clusters of galaxies, and all the way to the cosmic microwave background. Another sort of misconception that people have when discussing dark matter is that the term dark matter, you hear this quite often in conferences, the fact that the term dark matter was coined by Zwicky in the 1930s when he was doing analyzing the coma cluster. Now we've been working quite a lot with some professional historians at the University of Amsterdam who study the history of physics and the history of science in general. And I put two references up there for those of you who are curious to know more. But basically we were trying to trace back in the scientific literature the use of the phrase dark matter. And it turns out that even 30 years before Zwicky, people were discussing dark matter in the very same, with the very same meaning that Zwicky had in mind when he was analyzing the coma cluster. So in particular, Lord Kelvin, in 1904, was discussing in a very sort of modern way, he was trying to associate the velocity dispersion of stars in the universe, that in 1904 meant the stars in our own Milky Way. We didn't even know that there were external galaxies in 1904. So he was trying to associate the velocity dispersion of these stars, the observed one, with the total gravitational potential in the galaxy. And he was trying to, he made a point that many of our stars, perhaps a great majority of them, might be dark bodies. And this was picked up a couple of years later by Poincaré, who really used the phrase dark matter already more than 110 years ago. Because it says that this method gives us the total number of stars, including the dark ones. And since this number is comparable to that the telescope gives, and there is no dark matter, or at least not so much as there is of shining matter. So they were setting already constraints on the local abundance of dark matter in the universe. Of course, the modern problem of dark matter is very different. We don't think about dark stars. We know actually that dark matter cannot be made of stars that do not emit light, that we're not able to see with our telescopes. But these are really the roots of the modern problem of dark matter. So we're not, say too much about that. Actually, we're not talking about the history of dark matter anymore. But we've been working quite a lot on this. So if you have questions, please take a look at those references, or I'll be happy to answer your questions after the colloquium. Let me start then with presenting some more recent results, which is what I really would like to try and do today, to present some fresh results to show you where the community is going and where the field is going these days. And let me start from the distribution of dark matter in the Milky Way, in our own galaxy, which is relevant actually for the searches for dark matter. It's called direct and indirect detection of dark matter. And the first thing I want to do is to look really around us, to the stars in the solar neighborhood. And I want to ask the question, can we get evidence for dark matter locally, essentially, where locally in this context means volume of, let's say, 100 parsecs or something like that in the vicinity of the sun. And the way you do this is very similar actually to what people were doing in the very early times, so through the 1920s and 1930s. with the pioneering work of people like Kapteyn, Oort, Jeans, and so on. And we write down an equation, basically. So if you ignore for the moment the first term of this equation, which is the so-called the tilde term, but if you look at this part of the equation here, what this is telling you is that you can associate the gravitational potential, particularly the derivative of the gravitational potential, with respect to the vertical direction, with respect to the disk of the galaxy, to a measured velocity dispersion of stars, once you know the density, the number density of a tracer population of stars. So this is a way of connecting some observables, like the density and velocity dispersion of stars, with the total gravitational potential. That includes a contribution not only by the stars, but also from the dark matter. Now this has been used for many years to try and get constraints on the local gravitational potential. And this is a review article that was published in 2014 by Justin Reed that has collected basically the results of different analyses of this type that have been performed by many people studying. So if you look at the upper panel, you see that it starts in 1920 and it runs all the way to today's measurements. And this is a zoom in of the past, the activity in the past 20 or 30 years. And you see that most of these measurements are kind of converging towards like a common value. And depending on whether you're an astrophysicist or a particle physicist, you might want to read this, the units in a different way. So for a particle or an astroparticle physicist, this is usually expressed in GeV per centimeter cube, and this is of order 0.3 or 0.4 GeV per centimeter cube, the local density of dark matter. And in units of, for astrophysicists, this is of order of 0.01 solar masses per parsec cube. And we're getting more and more observational results that are allowing us actually to reduce this uncertainty, at least the statistical uncertainty in a pretty substantial way. And this is a recent analysis we performed with a PhD student in Amsterdam, Hamish Silverwood, who's actually now in Spain. He's working in Barcelona in the Gaia group. Basically, we studied what kind of uncertainty you can set on the local dark matter density as you increase the number of stars that you can measure in the solar neighborhood. So if you increase it from 10 to the 4 to 10 to the 5 to 10 to the 6, you see that the statistical error decreases with the number of stars, as you would expect. And the next challenge is really to understand systematic errors. So what terms you should keep into account when you write down your Jeans equations, and in particular how you couple the vertical dispersion of stars with the velocity dispersion in other directions. So this is what concerns the local density of dark matter, which is relevant for direct detection experiments. You can also look at the galaxy on much larger scales, so all the way from the center to the outer parts. And this is a distribution. This is the measured angular circular velocity of stars and gas, so different traces of the rotation of the galaxy, as a function of the distance from the center of the galaxy. And you see it starts from 2.5 kiloparsecs, which is the size of the bulge at the galactic, the inner parts of our galaxy. We are sitting about 8 kiloparsecs away from the center. And this plot goes all the way to 20 kiloparsecs, the outer parts of the galaxy. What you see here in red are measurements of different traces of the rotation curve. And what you see with the black line is the rotation curve that you would get in the galaxy if there were only baryons, only stars and gas that we observe. Okay? And the gray region around that black line shows the uncertainty we have on the contribution of baryons. Okay, so the point I want to make with this plot is that even by eye, you see that you need some additional component of matter if you want to explain the rotation curve of the Milky Way on top of the stars and the gas we observe. Now you can put this on more solid grounds by performing a statistical analysis. First of all, let me show you the residuals, so the data minus the prediction. The black line is our fiducial model there for the distribution of baryons. And you see that basically, if this is the zero line, where in principle the data would match the model if they were agreeing with each other, you see basically that there is an excess, that the data basically overshoot the circular rotation velocity at all radii, essentially. And the other point I wanted to make is that this dashed line that you see over there is basically the contribution that you would get from a dark matter component in the Milky Way. And this is not a fit to the data. This is just what you get if you simulate a galaxy like the Milky Way. So this is so-called a vanilla Navarro-Franken-White model. So even if you don't try to fit the data at all, if you just overplot what people typically use for describing the dark matter distribution in the galaxy, you see that it naturally goes through all the data points without even trying to fit them, basically. And you can ask the question, for each of the models that have been analyzed that have been shown in the upper part, you can show what is the evidence, the statistical evidence, that you have an extra component to the gravitational potential that we interpret in the context of dark matter. And basically this evidence goes above, sorry, you can't see where it is, this is the phi sigma line. You see, basically for all the models, you get more than phi sigma evidence of the need of an additional component in the galaxy if you want to explain the rotation curve. Now if you put this in a more, in more technical terms, and you try to constrain what is the local density of dark matter. This is a crucial ingredient for direct detection, for direct dark matter searches. And you put on the vertical axis the slope of the dark matter profile, so how steep the mass density profile of dark matter is when you go towards the center of the galaxy, which is the quantity which is relevant for indirect dark matter searches. You see that for each of the baryonic models that we considered, so let's start first from the black solid line, which is the one corresponding to a fiducial model. You can constrain at the 2 sigma level, what is the local density, quite precisely. And if you change your baryonic model, so if you consider any of these 70 baryonic models that we considered in this paper, you see that the local density doesn't really change much. So the systematic uncertainty on the local density is not that large. What changes a lot is the slope of the dark matter profile, right? So if in particular you look towards the center of the galaxy, the distribution of dark matter in those regions is very uncertain. So if you change from one model, which is down here, to a model which is up there, you get basically a variation of the slope of the profile, which goes between 0 and 1.5. And this is a power law, going all the way to the center, so you get an enormous uncertainty on the amount of dark matter at the galactic center. So how can you estimate, and we will come back later to this point, how can you estimate the contribution, the amount of dark matter at the center of the galaxy? You typically run numerical simulations. And is it possible to turn down the lights a little bit? Because I'm not sure it will show otherwise. If it's easy, Mariam, otherwise, I wanted to show you a movie of a numerical simulation called the Illustris simulation. And what you're going to see is basically okay, that's perfect, thank you. Yeah, only for just 1 minute. What you're going to see is basically the evolution of structures in the universe starting 500 million years after the Big Bang. So at this stage, the fluctuations that were present in the early universe and that you see basically captured in the cosmic microwave background have started to grow bigger and bigger structures under the pool of the gravitational pool of dark matter. And in numerical simulations these days, they can follow how dark matter structures grow. We're now 2 billion years after the Big Bang. But they can also include the effects of baryons in the simulations. And this is what has happened over the last 5 to 10 years. If you follow one of these big halos, you will see that some interesting activity will start to appear when you are like 3 or 4 billion years after the Big Bang. You see that you start to form stars in these systems. And when you start to form stars, these stars will explode and form supernovae. And then explosions of supernova will inject energy and metals, actually heavy metals in the interstellar medium. And this will affect actually the history of these halos. It will affect its dynamic and internal structure. So this is the new frontier basically in cosmology, in numerical cosmology, to try and capture basically the physics of what happens when stars form. And because this is a problem, what you're doing basically is you're trying to follow this phenomena in a box which is 100 megaparsec or 1 gigaparsec large, and you're trying to resolve physics that happens on very small scales, a parsec or a fraction of a parsec when stars form and inject energy and so on. So most of this is done at the subgrid level, which means that you provide recipes to form stars and inject energy produced by supernova, not by resolving this phenomena in your simulation, but doing this in a sort of an effective way. So you're trying to capture basically this behavior without really resolving these processes. Thank you. And we will come back actually to the point, to this point of why it is important to solve these processes on very small scales. So let me move on now to the dark matter candidates. So this was about, in the first 20 minutes, we discussed about the distribution of dark matter in the galaxy specifically, and I presented you some recent results about how we can try to measure things and connect things, not just using simulations, but really looking at the observational data we have about the distribution of matter in the galaxy. Now let me ask the question, what do we know about dark matter? And the way I want to discuss this is in the framework of a 10-point test that we put together with Marco Taroso, who's there. A while ago, was here at IFIC for a couple of years. So the question that we asked in this particular paper was, suppose that we asked the question, what are the properties that a particle should have in order to be considered a good dark matter candidate? And we'll not go through all these points because it would take quite some time to do that, but let me highlight some of the main points. So first and foremost, you wanted this particle that explains the dark matter to have the right relic density. Right? You want to form these particles in the early universe, to produce these particles in the early universe with the appropriate abundance in the universe. And this abundance is actually constrained at the percent level by cosmological observations. So this is the most stringent constraint probably that we have on the nature of dark matter. Then you want these particles to be cold, and this cold can be made very precise. They must be essentially non-relativistic at the epoch of structure formation. Otherwise, because of free streaming, they would erase structures on small scales. You want this particle to be neutral, so no electric charge, no color, nothing basically that would give it large interaction cross sections. You want it to be consistent with Big Bang nucleosynthesis and to be compatible with the structure and evolution of stars. And once you start to play this game, you will be surprised how difficult it is to propose a particle that doesn't modify substantially something in the universe. And then, the bottom row, you have constraints on the couplings of these particles. So the couplings of dark matter particles with itself. So about the collisionless nature of dark matter, you use systems like the Bullet cluster, the ones for those of you who are familiar with it. You want the couplings of this particle with the standard model to be, with the standard model particles to be small and compatible with direct detection experiments. We will come back to this point in the second part of this presentation. And then points 8 and 9 are connected with the so-called indirect detection of dark matter. You don't want this particle to produce any radiation, basically, any gamma rays, any synchrotron, any neutrinos, nothing basically that would violate current observational constraints. And then the 10th point in this test, we asked that the dark matter should be probed. The dark matter particle should be it should be possible to probe the nature of dark matter, at least with a thought experiment that you can perform even 100 years from now. But the idea is basically that you don't accept a solution that is a particle that is only interacting gravitationally with the standard particles of the standard model. Otherwise, all the experiments you could perform, you've already performed essentially. Right? So you hope that at least in principle, nature was kind enough to produce a particle that is possible to probe. Now, this doesn't tell us. This is a set of constraints, but it doesn't tell us specifically what dark matter is. And I wanted to make, before moving to the list of possible dark matter candidates, I wanted to make, to pause for a second and make a few points which I think are important. The first one is that if you take general relativity and you take, put in the stress energy tensor, you put all the particles of the standard model plus one species of cold and collisionless particles, you can explain most of the cosmological observations. Okay, and these includes highly non-trivial tests like the cosmic anisotropy spectrum, baryonic acoustic oscillations, weak and strong lensing, rotation curves of galaxies, and so on. Okay, so this is an important point to keep in mind. And I think that the cold dark matter paradigm is by far the simplest and the most complete explanation for this phenomenon. Now you can ask the question whether the lambda cold dark matter is able to explain all observations that we have in cosmology and astrophysics, and the answer is no, or at least not yet. And in particular, there are issues on small scales, small cosmological scales, so let's say galactic and subgalactic scale. And some of you might have heard about the so-called cusp core problems, how steep the dark matter profiles are in the innermost regions. The so-called missing satellites, the fact that numerical simulations tend to produce more substructure in the halos than we observe. And the so-called too big to fail problem, the fact that these substructures seem to be, the predicted substructures seem to be too concentrated, basically, with respect to what we observe. So it's unclear whether we need a better understanding of dark matter physics, whether the baryonic physics that I was discussing in the context of numerical simulation might explain these possible discrepancies. And there's an enormous activity right now in trying to understand whether by modifying the properties of dark matter or by a better description of what the baryons do in numerical simulations, so how we form stars, how the energy of supernova fits back on the interstellar medium, you can resolve these issues. Now, I don't think you can read what this reference that I put here is, but I wanted to point out that yesterday, just also to show how rapidly evolving this field is. Yesterday, it was this paper was published on Annual Reviews. It's a paper by James Bullock and Bolan Kolchin, where they basically review this problem. It's called small-scale challenges to the lambda cold dark matter paradigm, and they discuss how we can help to solve those. And in general, and this is the only mention I would make to modified gravity in this talk. I think the way many researchers in the field see the current status of dark matter studies, I think it is right to continue to challenge the lambda cold dark matter model, and in particular, there are ongoing efforts to modify GR. So instead of having an additional component in the stress energy tensor of cold collisionless particles, to modify GR in the first place, so your equations for gravity. But you should never do this ignoring the evidence that we have from all this abundance of tests. So if you see a theory of modified gravity, if you want to put this on the same footing, basically on the same grounds as the lambda cold dark matter theory, you shouldn't be able only to explain one aspect of the dark matter problem. You should really ask for this modified theory of gravity to explain everything. It goes from cosmic macrowave anisotropies, baryonic acoustic oscillations, and so on and so forth. Now let's get to the important question: what is dark matter? And of course, nobody knows. There are many ideas about it. And to give an idea of the spectrum of possibilities, we're talking about something that could be on the scale of 10 to the minus 20 to electron volts in the case of the so-called fuzzy dark matter. We have axions, you've heard about those in the lecture colloquium a few weeks ago here. We have sterile neutrinos, are still an interesting and well-motivated possibility. Weakly interacting massive particles, so some neutrinos typically are at the keV scale. Weakly interacting massive particles are between, let's say, 10 GeV and 10 TeV. We have WIMPzillas, so very heavy version of WIMPs. And we have primordial black holes that occupy a mass range which goes from 10 to the minus, I think this here is like 10 to the 18 grams. And all the way here you have 10 or 100 solar masses, basically. Okay, so you have 90 orders of magnitude of uncertainty on the dark matter candidate mass. And it's important to realize that each of these models, each of these ideas, they come with their own phenomenology. They need dedicated experiments, and the height of the window corresponds more or less with the number of papers that are published on these candidates, the ones that have been published so far. So you see that most of the literature is dominated by WIMPs, but there are interesting also, there's a substantial interest also with axions and strong neutrinos. There's a growing interest again in primordial black holes. Now, for those of you who follow the field, it's impossible not to see all these headlines that claim discovery of dark matter, or they propose new ideas, and there's even since we're here in Spain, there's El País saying materia oscura más repelente que nunca. So I think it is important to keep in mind that the field, especially now, is completely open. Okay, so until maybe like 5-10 years ago, people would say, WIMPs is our best guess. Maybe it is still our best guess for the nature of dark matter, but we're going again in the direction where essentially anything goes, and we need ideas, we need experiments to move forward. And I think it's also useful to look at this by thinking that probably almost all of these ideas will turn out to be wrong, or at least it is possible that different species contribute to the dark matter density, but because most of them, they are produced with independent physical mechanisms, it's very hard to think that you would have a situation in which more than one particle will contribute similar amounts to the dark matter relative density. In which case, you would have like a leading candidate that provides most of the dark matter in the universe, and all the others will provide a subdominant contribution. So I cannot possibly review all that's exciting in this field, so I will try to narrow the discussion down to a couple of interesting candidates. I will first mention primordial black holes very briefly for like a few minutes, and then I will focus on WIMPs, on weakly interacting massive particles. And the reason why I want to briefly talk about primordial black holes is that this I think we need to take a very good look and close look at the data and observations in this field because of the dark matter is an underdetermined problem. We don't have enough data to discriminate among all these possibilities. So we need to confront ourselves with data and try to figure out what the data are telling us about the nature of dark matter. So one thing we know for sure now is that black holes with a mass of several tens of solar masses have been observed. The merger of two black holes of this mass has been observed in a very convincing way with gravitational waves interferometers. Okay, so this is the big discovery that happened last year. Estimated black hole masses are around 30 solar mass, and we could reconstruct the waveform and interpret the gravitational wave event as the measure of a binary black hole system. Now, this has prompted the suggestion that dark matter, that these black holes that we observe in there, are all of the dark matter in the universe. And in particular, this is possible if these black holes are primordial. So you cannot have dark matter in the form of black holes produced by stellar explosions, because you need to form stars first, and you know, dark matter cannot be made of baryons. You know, you have to, you know, separate dark matter from the rest of the matter in the form of black holes well before Big Bang nucleosynthesis, if you want these black holes to act as dark matter in the history of the universe. So this idea has been put forward like 40 years ago. There are papers by Sadovich and Hawking in the late 60s and early 70s, you know, trying to figure out how much black holes could contribute to the dark matter in the universe. But this turned out to be, you know, kind of an interesting suggestion, because if you now plot the fraction of the dark matter that can be formed in the form of primordial black holes as a function of the mass of these primordial black holes, you see that there are many constraints across the spectrum. But if you for the moment focus on the black line on this plot, let's see if I can show it with this. No, okay. Anyway, if you just follow this black solid line, and you see that it envelopes all the correct constraints, you see that in correspondence of 30 solar masses, there's a gap up there. I'm not sure I have a pointer, and, you know, I cannot reach over there. But there's no pointer, right? The laser pointer, anyone? Never mind. But if you look at the 30 solar mass, something that corresponds to here, all the way up there, and if you ignore these regions which are they correspond to like dashed lines, you see that there's a window in which you do not have any constraints, essentially. And this is, you know, this prompted the interest of theorists and cosmologists, because, you know, it seemed to be a window where you could explain all of the dark matter in the form of primordial black holes. So many people have played the game to try and provide interesting constraints on these objects. And I think one interesting way of trying to do this is to try and see, so suppose that this is true. Suppose that dark matter is in the form of black holes of, you know, tens of solar masses. Then if you look at the bulge of our own galaxy, at the center of our own galaxy, you should have, I mean, we know how much dark matter there is there. You know, it's more or less 10 to the 10 solar masses in dark matter. So you would have 10 to the 9 objects, like a billion masses, a million primordial black holes with a mass of tens of solar masses. So you can ask the question, what happens when these objects accrete gas? And inevitably, they would start to, you know, form an accretion disk, long jets, like, you know, we would think all black holes do. And you can calculate what would be the radio and X-ray emission associated to those. And just by, you know, making this calculation, you can convince yourself that you know, you should have observed these objects if they were there. Which is not the case. So there are two possibilities. One is that, you know, the modeling that we're doing of the accretion and the ensuing emission of these black holes is wrong. And this is, you know, a possibility because, you know, it's a very, very complex system. You have you know, objects moving at supersonic speeds in an interstellar medium. It's a very complicated problem to try and model. But even in that case, even if our calculation, the one that we published in that paper over there, even if it's less conservative than we think it is, even in that case, you know, future experiments like SKA, the Square Kilometre Array, should be able to observe this population of primordial black holes, even if they are a subdominant component of dark matter. So this is, I think, you know, a field which is worth keeping in mind because it's evolving very rapidly, and there might be something interesting there. In view of time, let me skip. You know, I had a couple of slides on spiral neutrinos. Let me skip them, and we can come back to this if you have questions. And let me focus the last part, the last 20 minutes of this presentation, on WIMPs, on weakly interacting massive particles. Now, the reason why everybody likes WIMPs is that you have a very natural way of producing them with the right abundance in the universe, in the early universe. And this natural way was a, you know, very simple 2-to-2 process, an annihilation of dark matter particles into standard model particles. The you just assume that this process is in equilibrium in the universe, so that the annihilation process can go in both directions. And you can write down the Boltzmann equation that regulates the number density of particles that are kept in equilibrium through that type of reaction. And this is like textbook cosmology. Essentially, you know basically that if they are in equilibrium because they are massive particles, the number density will be exponentially suppressed as the universe evolves towards lower temperatures. But at some point, the number density of these particles, stops decreasing and freezes out, because these interactions, the universe becomes so diluted that these interactions cannot happen anymore. Basically, on average in the universe, these particles cannot find each other when the universe becomes sufficiently diluted, and the number of particles in the universe, the number of dark matter particles in the universe would remain constant, essentially, on average in the universe. And if you solve this equation, basically under some simplifying assumptions, you see that the relic density is inversely proportional to the annihilation cross-section. The standard argument that people like to do is for an annihilation cross-section, which is at the weak scale, then you achieve the right relic density, which is of order of 4.1. Now, let's consider this possibility. There are different ways of testing this conjecture, whether the connection between the dark matter problem in cosmology and the weak scale in particle physics. And you can do this with indirect detection, so to search for annihilations that happen in overdense regions of dark matter in the universe. You can search it with direct detection, so for the scattering of dark matter particles of nuclei in a detector, or with colliders. Okay, so let's start with indirect detection. So what I want to do basically in the last part of this presentation is to go through indirect detection, direct detection, and accelerators, making some comments about what the status of the field is and how we can hope to make progress. So suppose that we start to see something, how can we reconstruct the properties of dark matter from those observations? So let me start with indirect detection. This is something that you can do, that you can work out almost on the back of an envelope. You can calculate, for instance, so assume that the wind paradigm is true, and assume that you have a cross-section, that's an annihilation cross-section, which is at the level 10 to the minus 26 centimeters cubed seconds minus 1. So like a standard weak interaction cross-section. Then you can write down an expression for the number of photons, for instance, that you would expect from any direction in the sky, given a mass of the dark matter particle and annihilation cross-section. And what you see in that expression is that you have at the end of the E that tells you how many photons are produced per annihilation. You have the annihilation cross-section. You have a very good guess for that from this WIMP miracle argument, and the mass of the dark matter particle. And then what you have on the right is sort of a counting of the annihilations that happen between you and a certain direction in the sky. So in particular, you integrate the mass density squared. Okay, so it's a self-annihilation process, so you have a square in the number density. And you can produce maps like this. This is we've been playing this game for many years now, many of us. And what you see, if this is the whole sky in galactic coordinates, you see basically that you have an excess, or a predicted excess of photons from the center of the galaxy. Right? So this is the galactic center with the supermassive black hole is and everything. And then you have a few substructures that appear where you will still get a signal to background, signal to foreground, which is very, very strong and very prominent. So this was a standard prediction for many years in the field. And then in 2009, something interesting started to happen because many people claimed that there was an excess of photons from the center of the galaxy. Okay, so using Fermi, the data from the NASA Fermi satellites, a number of authors they started to observe an excess of gamma ray photons from the center of the galaxy. And this was an excess on top of the expected astrophysical emission. So the question was, is this a signature of the fact that our models for the astrophysics is not good, or is this a signal of dark matter annihilation happening there? So many people have tried to disentangle two contributions. One thing that was noticed very soon was that in order for this to account for, in order to explain this with dark matter, you needed a distribution of, you remember at the beginning of this presentation we were talking about the slope of the dark matter profile towards the center of the galaxy. You need a profile which is very steep. Okay, so we tried and because observations are not very good at constraining that possibility, we looked at numerical simulations, in particular the EAGLE simulation. Nice thing is that with these simulations you can form galaxies which are kind of quite similar to the one of the Milky Way. We selected galaxies that were similar to the Milky Way in terms of rotation curve. Okay, so we matched the halos that look like the Milky Way to the rotation curve data that we have in order to select objects in the simulation that really look like the Milky Way. And what we got out of it was basically a scenario in which the data of the excess, this is the energy spectrum of the excess, they typically overshoot the theoretical prediction. In other words, the profiles that you get from numerical simulations, they are not steep enough to explain the observed excess. Okay, so this was kind of, this seemed to go in the direction of saying, it's very hard for dark matter to explain this excess. And then a number of other papers were published where people basically looked at possible contributions from astrophysical sources to the excess. And there are 3 articles that came up with a similar solution basically for this problem. So in this particular analysis, for instance, they were looking for the contribution to this excess that comes from unresolved point sources. And they found out that most of this excess could be explained by those. Okay, so, and if the emission is not diffuse, as you would expect from dark matter, but it comes from many unresolved sources, then this means that this is not due to dark matter, but a new population of astrophysical sources. So how do we make progress? The only way for making progress is to compare different annihilation channels. And Juan Jose, who's probably here in the audience, maybe not. So anyway, he's pointed out kindly this recent paper published by the Antares collaboration, where they put on the same plot the constraints that you get on an annihilation cross-section coming from different experiments. So IceCube and Antares that search for neutrinos, including neutrinos from the galactic center, Fermi and Hess. And so without going through the details of this, I just wanted to point out that complementary constraints exist from different experiments and different channels. So if we want to, I don't think we have convincing evidence of dark matter from the galactic center, but if we ever find convincing evidence from one channel, probably the only way of convincing ourselves that we found something is by correlating this with the results of other experiments. Now let me move on quickly to direct detection. The idea is very simple. You build a detector and you wait for a dark matter particle to interact with one of the nuclei in your detector. Very simple to say, very difficult to do. These are extremely complex experiments. And if you want to visualize what happens in a detection experiment like this two-phase xenon experiments, the idea is that you have some liquid xenon in a vessel, and then you have a layer of gaseous xenon on the top of it. And there's an electric field which is applied on this vessel. Now, if you have particles, background particles like electrons and photons, entering your detector and interacting typically with the electrons around the xenon nuclei, they produce a prompt signal, which you see shown here, which is picked up by your detectors. And then when the electrons drift in the layer of gas up here, because there are many of these electrons, they produce a flash of light, which is even more intense. If a particle like the dark matter interacts with the nucleus, the number of electrons that are ionized in the interaction is much smaller. So by comparing this initial signal, this S1, corresponds to the initial collision, with the S2, which is this secondary signal that is produced by the electrons that drift up in the gas layer, you can discriminate these interactions with electrons from the actual events you're interested in, which are the events, the interactions with the nucleus of with xenon nuclei. So just like we did for indirect detection, you can write down an expression for the rate of events that you expect. And again, this is a typical astroparticle experiment. So you have a mixture of, in yellow, quantities that depend only on the particle physics of the problem, like the mass and the differential scattering cross-section of points of nuclei. And then you have quantities that depend on the astrophysics in cosmology, which are the local density, which we discussed in the first part of this presentation, and the velocity distribution of these particles. And just by integrating this, you get an expected rate. And the field is evolving very fast. This is a paper, the paper published by the Xenon 1-ton experiment, where they got the most stringent limits for, at least for heavy dark matter particles. It was published in May, so last month. And this is how the current constraints look like. So this is the paper I just mentioned. You see that they got to incredibly small cross-section. This is an exclusion plot. So if you look at the black line, this excludes cross-sections higher than was shown by the black line. And you see that for masses which are comparable with the mass of the xenon nuclei, you get a cross-section which is incredibly small. It's the level of 10 to the minus 46 centimeters squared. What is the future of this field? Well, we are more or less up here. Remember, we are 10 to the minus 46 right now. There's still a gap of a few orders of magnitude, let's say 3 orders of magnitude, before we reach the so-called neutrino floor. In these experiments, we start to pick up the neutrino coherent scattering, the neutrinos produced by the sun or supernovae in the universe that would coherently scatter with the nucleus of your detector. And this is an estimate of where this neutrino floor will be. If you want to go below this neutrino floor, then you have to be smarter. Basically, you have to do something else. You have to use directional detection and so on. So the future of this field, at least for the next 5 to 10 years, is to try to go down as much as possible in this plane and to try to get as close as possible to this neutrino floor. What happens if you see something? Then you can try to reconstruct the properties of your dark matter particle. But the price, so this is a reconstruction performed for 3 different benchmarks. So this is mass, scattering cross-section, and you see that depending on where you are in this parameter space, you will be able to reconstruct masses and cross-sections with a different degree of precision. The key point is that you have also well, there are 2 problems. One is that you have to assume that the particle that you have discovered is the dark matter particle in the universe, because you need a rho, a local density in the expression of the rate. So if you want to use a number for that, you need to specify what the local density of this particle is. And the second point is that if you also include astrophysical uncertainties, you get something which is, if you compare the 2 plots, this is without astrophysical uncertainties, this is including astrophysical uncertainties, you see that the contours blow up significantly. So even if we discover something in these experiments, we will need additional information to convince ourselves that the particles we've discovered are the dark matter particles in the universe. Okay? Because it's a perfect degeneracy between the cross-section, the scattering cross-section that you see up there, and the amount of particles that we have locally in the galaxy. In the last 5 minutes, I want to say something very quickly about the Large Hadron Collider. There are experts here. So, and we've had the colloquium by Andreas Hucker about searches for beyond the standard model at the LHC. So I will not spend too much time on this. What I wanted to do is well, I hope you relax for like 30 seconds while you watch this movie before I comment on the last few slides. But the idea of colliders, at least to an astroparticle physicist, or a person who tries to combine different detection strategies together, the way we look at this is basically, we have high energy protons colliding in these big detectors. We will analyze the outcome of these collisions, search for new physics. And what we want to do is to search for, in particular, for the, at least one possible way of doing this, is to search for weakly interacting massive particles. The idea being that if you have all the particles of the standard model in the bottom part of this plot, in red, you have your quarks, the leptons with the neutrinos, and the gauge bosons. In the mind of many people who do beyond the standard model, the idea is that you have a new layer of physics that you hope to get access to by increasing the energy of your collisions. So suppose, for instance, you produce, by colliding quarks, you produce color partners, you produce squarks or neutrinos or whatever. Then you can follow the decay of these particles from there all the way to the lightest particle of your theory, which is the dark matter candidate. And you can do this by searching, for instance, for missing energy in your detector. Now, as you've heard, there's no sign of new physics. But there are supersymmetry searches, which supersymmetry was for many years, and maybe still is, the leading candidate for an extension of the standard model. All these searches have not yielded any result. The result that they yielded is that everything seems to be consistent with the standard model of particle physics. But it's also true that we are just at the beginning of a very long journey with the Large Hadron Collider, and this is a plot of the luminosity as a function of time, and we are here in 2017. And if you follow the predictions for what we're going to get in the next 2 decades, we have only collected only 1% of the data that will be eventually connected. What I want to do is basically to ask one specific question that allows me also to connect with what I was saying about the other searches. Suppose that you see something eventually at one of these, with Atlas or CMS. You start to see departures from the standard model, and maybe in one of these signal regions that you build in order to search for new physics, you start to see excesses. Now, what we've been doing in the past few years was basically we learned how to go from a dark matter particle model to the data. We made prediction and forecasts for many years. Now, eventually, what we would like to do, and this is quite a complicated thing. It involves generating particle spectrum, calculating cross sections, generating events, and performing a detector simulation. Eventually, what we want to do is to go from the data to reconstruct the old particle model, and in particular try to identify the dark matter nature of these particles. And the way we have to do this is by walking essentially in the parameter space of theory. If you want to go from data to model, what we need to do is to do many times, up to 10 to the 9 times, depending on the specific model you have in mind, to do this forward modeling, and to walk in the parameter space of your theory to search for models which are compatible with the data. And that's a very, very expensive procedure to do. Eventually, what you would like to do is to go from, suppose one day you start to observe a particle spectrum, you want to go to your model and to reconstruct how much of these particles, how many of these particles you have in the universe. Right? If you can start it from LHC data, you can reconstruct the radiative density of these particles and prove that this radiative density matches what you observe with cosmological observations. Then you validated your particle physics model and your cosmological model. Okay, so this would be a fantastic dream scenario. Unfortunately, this is probably not what you're going to get. And this is a work we did a few years ago with Roberto Ruiz de Austri and a few other collaborators. But we showed that we try to work out a specific example, a specific benchmark. We try to work out the complete reconstruction procedure, and what you get for the posterior is not this very nice and clean Nabel Gaussian that you were hoping to get in the previous slide. It typically exhibits multiple solutions, and the peaks are very broad and very uncertain. And the reason is that the problem is under constraint. You don't have enough information from the LHC to constrain the properties of these particles. So if you now put the omega h squared, how much dark matter there is in the universe on the x-axis, and the scattering cross-section on the vertical axis, then you see that the problem is under constrained, essentially. The good news, and this is the last point I want to make, is that if you add the information that comes from direct detection to this reconstruction, then things look much better. And in particular, if you look at what happens when you include direct detection, you see that you break the degeneracy along a specific direction. And when you perform the combined analysis, then you can pinpoint the right solution much better, and therefore your reconstructed relic density looks much more consistent with your expectations. And this is my last slide. I just wanted to point out that to perform this in a reliable and self-consistent way, you need to go beyond the current approaches for global fits, and you really need to use some of these big data tools, these machine learning tools, to explore in an efficient way these multidimensional parameter spaces of beyond the standard model theories. And this is a work that we're doing in collaboration with Roberto, who is the Austrian, who's really one of the leaders in this field. And I don't have time to discuss this in any detail, but if you're interested, feel free to ask questions. I'll be happy to tell you more about this. So these are my conclusions. There's an extraordinary theoretical and experimental effort to identify dark matter. There are many interesting ideas. The field is completely open right now. I think it is important to keep in mind that there's no guaranteed discovery for any of the experiments that we're performing. But many experiments, the good news is that there are many experiments which are currently running or planned, and just by looking at the data and what data are telling us, that we can understand in which direction we should move to identify dark matter. And the effort is not wasted, even if you don't find dark matter within direct detection or direct detection. This effort is not wasted. For indirect detection, we're probably discovering a new population of astrophysical sources at the center of the galaxy by analyzing this GeVXS. We might be able to detect the coherent scattering of neutrinos with these direct detection experiments. So it often happens in physics. Every time you perform new experiments or you test new ideas, you get interesting results, even if sometimes they're different from what your expectations were at the beginning. And the other point I wanted to make is that it's important to think strategically also about how do we identify these particles, and we also want to test for possible multi-component scenarios, and also to allow precision tests of cosmology. Thank you.
So now we have some time for questions.
Well, thank you very much for the interesting summary. So I have a question. How big is the uncertainty in the estimation that we have for this neutrino flow? In particular, I can imagine for large masses, because I could imagine that for many solars are more controlled, but the supernova part and all these things is...
I think it's fair to say that the order of magnitude is known, but I don't have an exact number, but I would guess there's a factor of a few on that when you go in the part where the supernova background would dominate the contribution to the neutrino flow. As you say, for what concerns the low energy part, the solar neutrino flux is much more constrained.
More questions?
So you said that direct detection can solve the degeneracy. So you need to assume something about the local energy density and the global one?
That's right, yeah. So the way you do this is by assuming that if you have, so let's talk about neutralinos, just to give a specific example. You have to assume that the neutralinos that you've discovered with your accelerator contribute to the dark matter locally, so in the 100 parsecs around us, as much as they contribute on average in the universe. Okay, so if they contribute 10% of the local density, they contribute 10% of the average relative density in the rest of the universe. And so we tested this with numerical simulations. So if you have, if dark matter is cold, and we know the neutralinos are cold, but even if there is an additional component that's cold, then that's verified to very with very good precision that there's similar contribution. If dark matter is warm, so if you have a different velocity dispersion in dark matter than you would have for these very cold neutralinos, you can have departures, but they're never departures by orders of magnitude, because otherwise you would violate other constraints. So it is an assumption when you perform that combined reconstruction, but there are good reasons to believe that there's not a very strong assumption actually, that it is fulfilled by any particle which is a dark matter.
Thank you, Antonio, for this transfer view of the problem. I have a provocative question. Okay? Up to now, all the evidence for dark matter is from gravitational interaction. What if, besides the possibility of primordial black holes, one has as dark matter particles in the sense of particle physics, but with only gravitational interactions? What to do?
No, there was the kind of nightmare scenario that was alluding to in the point 10 of this 10-point test. We have to hope that nature was kind enough with us, so that we have a handle on the dark matter problem. Even in the case, say, we have to hope that even in the case where this is a particle that only interacts gravitationally, then we have other handles. So in the case of primordial black holes clearly interact gravitationally, but because of the strong field and so on, they can accrete matter and produce some form of radiation. If you postulate a candidate, so it would be very much equivalent to say, in dark energy, there's always this effort to discriminate dark energy from a cosmological constant, right? If dark energy is a cosmological constant, so something on the left of your Einstein equations, you've performed the experiments that you could perform. So the only hope to make progress is to have a theory which is convincing enough for you of why this cosmological constant assumes that the specific value. In the context of dark matter, if a particle interacts only gravitationally, then you've performed all the experiments you could do. We have gravitational evidence of dark matter. As I was saying at the beginning, we need to hope that nature was kind enough with us to give us a handle on this problem.
Maybe one possibility is the collider having the missing transverse energy as a result of a chain of decays in which at the end there is nothing else.
Precisely. So, but in that case, you would have a handle, right? If it is a gravitino, for instance.
No direct or indirect detection.
That's right. I mean, if this particle comes with a series of other particles that can be produced in detectors, then that's certainly the way to go.
So any other question?
Anyone? Thank you. So you were showing at the beginning, this plot comparing, the slope and the local density. So you were testing different models, but these models, seem to cluster in different regions. This because some intrinsic kind of types of models.
It's because of the way these models were constructed. So basically, they combine different assumptions on how matter is distributed in the bulge and in the disk of dark matter. So basically, they were clustering around 3 different models for the bulge in that particular case. But there's no other physical meaning about it.
More questions? there are no more questions. Let's thank the speaker again.
Thank you.